The broadcast is now starting. All attendees are in listen-only mode.
Do that on the right side of the panel. Can everyone hear us okay? Okay, well, we'll get started. Hello, everyone, and welcome to the Octopuz and Yaskawa Motorman Welding Technologies webinar. Thank you for joining us. Today we have two presenters, Tyler Rudnicki, our software account manager here at Octopuz, and Will Harlows, integrator sales manager at Yaskawa Motorman Canada. This webinar will be about 30 minutes long. If questions arise throughout the presentation, you may type them into the chat on the right side panel. We will address all questions through email shortly after the webinar is completed. Tyler, would you like to start us off?
Absolutely. Thank you, Natalie, for the introduction. Welcome to the joint Octopuz and Yaskawa Motorman webinar. I'll begin by presenting a background on Octopuz and then dive straight into a live demo. So Octopuz is a Waterloo-based company that develops, supports, and sells offline programming software for industrial robots. If you're unfamiliar with offline programming, it simply means the robotic program is developed on a computer instead of by manually jogging the robot point to point and recording the positions. A simulation and program are created in Octopuz on a PC and checked for potential robot errors such as singularities, joint limits, and collisions. The user would then create the robot code and transfer the code to the robot, commonly using a USB or Ethernet connection. Many companies choose Octopuz because of the extensive library of pre-configured components, local support, and the ability to simulate and create code for multiple robots interacting in a single simulation. The amount of time and money that can be saved by avoiding manual robot teaching is substantial. I will now get into the software and show you the extensive catalog of Yaskawa Motorman components, how easy it is to assemble robotic systems, and finally really dive into the welding functionality available in the software. As you can see on my screen here, I have now opened the Octopuz software. On the left is our e-catalog of components. This catalog is a web-based catalog that's constantly being updated. So all of these components are being readily developed by our application team as Yaskawa Motorman comes out with new components. So as you can see, there's robot positioner gantry systems, a variety of robots from welding to material handling, pick and place, as well as collaborative robots, and workpiece positioners varying from headstock tailstocks, tilt-turn positioners, as well as skyhook positioners. So I'll very quickly bring in an EA1400N and attach a torch to it so that you can see how we attach components in our software. Now once you drag components out of the catalog, they come in with all of the correct characteristics. So if I interact with my Motorman robot, it will stop at all the correct joint limits and will interact the way that it would in real life. If I wanted to connect my torch to my robot, I simply drag it close and it snaps to the end of the arm. Now as you can see, this is a very powerful tool to assemble components. I can also move my components around in the simulation in an XYZ coordinate system and rotate about those axes as well. And this can help me lay out an entire system, including positioners, walls, and a variety of different cell components. So now I'll bring in a cell that we have created for a customer, and I'll go through some of the welding functionality. All of our welding functionality is housed in this Weld tab. In here, you can do anything from collision detection to singularity, speed, acceleration checks, as well as posting the actual welding code. So what I'll do is I'll start by creating a home position. I will now index the positioner so that I can access the seam that I would like to weld, and I'll drag my robot over to my component using the purple circle. This allows me to snap to geometries, and then I can grab my blue arc and rotate my torch, and grab the blue arrow and move in the Z direction, and the green arrow to move in the Y direction. And I will use this as a clear position. Now to generate welds, I simply start the generate weld function, and this will bring up our welding functionality. All of our welding features or parameters would be housed in here, anything from stitch welding, touch sensing, multi-pass welding, or coordinated motion. We can also save and load recipes, and I will load the recipe for my first weld. So I'm going to create the weld now, and in our software we'll be prompted to select a floor surface as well as a wall surface for our weld seam. As you can see, the software has created an approach as well as a departure move and the variety of clear moves in between. So if I simulate through, you can see that the robot's going to move in, weld the seam, and automatically flare into the corner to avoid a collision with the wall. Now from here, I'm going to create a weld using laser touch sensing using the AccuFast laser. So I will load my touch sense recipe. In my search tab, I will turn on a 2-point touch at the beginning and a 2-point touch at the end. And again, I'm going to select my floor and my wall. And if we simulate through, it's going to weld the first seam and it's going to use my laser tool center point that I didn't turn on. So I'm just going to send my output to the laser to turn the laser on, and then send an output after to turn the laser off. Now it'll use the laser for the 2-point touch sense. Return to the beginning of the seam and weld the seam using my correct tool center point. Now from here, I'm going to copy my first clear move and drag it down to where I would like it in my program editor. I'm going to rotate my positioner to 90 degrees so that I can access the next seam that I would like to weld and create another point. From here, I'm going to use my positioner to weld around this seam. So I'll open up my generate weld again, load my recipe for my body to flange, and I'm going to turn on Smart Weld, which allows me to weld around corners. And with my positioner, I'm going to set it to width bisector. Now again, I'll select my floor and the wall of my seam, and the robot will create that motion. If I wanted to walk through to make sure that my robot is going to follow the correct seam that I would like to use, I can walk through each individual point and see that the robot is moving around the corner, as well as using the positioner to position the component. After returning to the top, I will now do a V-groove weld using through-arc seam tracking. I'll load that recipe and go to my Process tab and turn on seam tracking. Again, selecting the floor and the wall of my seam. And now I'll simulate through the entire process. So the robot will come in, weld the first gusset weld, move around to do the 2-point touch sense, weld our seam, rotate into our 1G welding position, and use my positioner to maintain that orientation. And finally, use ComArc through-arc seam tracking to weld my V-groove. And as you can see, the weave itself for seam tracking is simulated, so you can accurately see whether or not the nozzle is going to be in contact with the walls of your component. And again, the torch will automatically flare into the end of the seam to avoid a collision with the wall. I will now pass the presentation over to Will. He will talk to you about some of the seam finding and tracking options available from Yaskawa Motoman. As we all know, production parts are never exactly the same as the CAD or drawing. For that reason, it's important to use seam finding and tracking technologies in conjunction with offline programming to overcome the differences from the simulated environment to real production parts.
Awesome. Okay, well, thank you, Tyler. As Tyler has already alluded to, there's a need to find the part that we've simulated. Essentially, what Octopuz does is creates an offline program that creates everything we need to weld out the part, but it's based on the part model, the virtual part itself. The tacked assembly that we're going to present to the robot will inevitably vary from the model to a degree that the robot won't be able to weld it out. The robot requires that the parts repeat, in essence, plus or minus 20 thou, half a mil, basically half a welding wire diameter, in order to ensure that we're going to successfully do so. So we need to develop strategies and utilize technologies to overcome this. So the first slide here shows sort of a summary slide of all the technologies available to us. Above the line is what we call seam finding. So before we initiate the arc, we're going to go in and find the weld joint. This varies from very simple touch sensing, where we're putting voltage on the wire and then jogging the wire towards the part until it grounds out, voltage goes low, and we can determine where the planes of the weld are, all the way to a laser line scanner, the Moto-Eye SF, which does a quick sweep of the joint and determines its geometry and location from that sweep. Then we'll get into seam tracking. There's two basic technologies available there. The first one, COMARC, as Yaskawa Motorman calls it, or across the industry known as through the arc seam tracking, where we're taking advantage of constant voltage welding phenomenon to track the joint. And then the higher end of the tracking is using what's called a MotoY LT, where we're using, again, a laser line scanner, but the difference being in real time while the arc is lit, we're going to track the joint. So seam finding, we've lumped both touch sensing and what we call AccuFast onto one slide. From the robot's perspective, these are identical in terms of the communication, the I/O required to make both work. It's the sensing technology itself, the transducer that changes between the two. Touch sensing has been around for decades. It's a very, very simple, robust process. What we do is we position the robot above, adjacent to the part. We send a signal to the welding system to turn on its touch sensing mode. And all of your modern welding packages, be they from Miller, Lincoln, Fronius, ESAB, whomever, will have a touch sensing circuit that we can access. What the weld package does is puts 80 volts on the MIG welding wire, and now we can jog that wire towards the part. When we make ground, we see the voltage go low, and we found the horizontal plane, for example, in a horizontal fillet. We can back up to some point adjacent to the part and jog laterally till we hit the vertical leg of the weld. Interpolate where the origin of the weld is. If you were to do this at the start and finish of the weld and draw a straight line between the 2 points, you would have found the weld. So a quick video here of touch sensing in action. What's going to happen here is the robot's going to come down and find the Z-axis dimension of the 12 o'clock point on the large piece of pipe, and then come over and do a couple touches on the nipple before it welds it out. So another point made on this slide here is there's some hardware a couple items of hardware we have to package along with touch sensing to make it work effectively. One being what we call a wire brake. So there's a pneumatically actuated plunger that's in the welding torch. And before we go into a touch sensing mode, we activate this brake. What it does is it prevents the MIG wire from cycling in and out of the contact tip and moving around on us as we move the robot. Once we've braked the wire, we go over to what's called a wire cutter and clip the wire to a known stick out. So the distance from the end of the contact tip to the end of the wire is known. And with that, we can do reliable touch sensing routines. So AccuFast, again, this is from a control standpoint, the same thing as touch sensing. What changes here is the transducer, the way in which we're finding the surface of the part. Here we've gotten rid of using the weld wire with voltage on it and replaced it with a spot laser. We set up a predetermined focal length. And again, we jog the robot from a nominal position above the part towards the part. When the focal length is met, we can see that signal go high, and we know that we found the plane of the weld. So we do that for both a horizontal and vertical leg in the case of a fillet or a lap weld, and carry on the same way we would with touch sensing. So the hardware involved here is the whole thing is based upon a key and spot laser. We put it in a hardened enclosure with a pneumatically actuated flapper that we can close to protect the emitter and receiver of the laser while we're welding, keep all the soot and spatter and whatnot off of it. Quick video of AccuFast at work. You're going to see two things happening here. The robot is first of all going to scan the back edge of the part and the left edge of the part. The part has not been fixtured to the table it's sitting on. It's been placed nominally. So the robot's going to do a sort of a macro location of where the part is at. And then it will do a function we call relative job, where it will shift and rotate all the points in its program to match this revised position. Then the robot will swing around and do a AccuFast tracking of the front of the part, and then do a mock weld of the part.
This is an AccuFast demo for C&P. Going to be tracking this weld seam here. This is how the part's set up. job. Robot first finds the user frame using relative job. Then using the edge macro to find Y. Then another edge macro to find X and Z. And then they're going to shift off of that user frame.
Yeah, sure.
Then I'm going to pause the program, and I'm going to move the part. I'm actually going to rotate it, twist it a little bit. Okay. Run it again. Finding another user frame. I had to put this piece on here because I wasn't searching this bevel very well. Edge macro again, finding Y, and another one finding X and Z.
Okay, so we get the idea there. So to compare the two, touch sensing, positives of that, it's a very low cost adder to the robot package. We generally charge $3,000 US for that to be added to the basic robot package. Very reliable, very easy to program. We've been doing this for decades. Our techs understand it very well, and it's very easy to explain to our customers how to set them up. The difficulties with it is it's typically slower than it's one of the slower finding technologies because we have to move slowly. If we move too fast, we'll end up bending the wire, losing our tool center point, and defeating the whole purpose of doing the seam finding. The wire clipping that's involved to cut to a known length, they'll also chews up cycle time. So AccuFast, by definition, was developed to be a faster alternative to touch sensing. So the positives of that are we no longer have to clip any wire because we're not using it. It's very easy to program. It programs more or less the same way as touch sensing programs. We can actually do our search routines much quicker because we don't have to worry about bending a wire. We can also handle thinner material. So in a lap weld, very difficult to pick that up with touch sensing, but AccuFast has a much better chance of picking it up. I guess the cons of it are that we would charge about $6,000 as an adder price for the AccuFast, and it can be sensitive when using super reflective, highly reflective materials, polished stainless, aluminum, whatnot. Typically how we package this out is we would sell both the AccuFast and touch sensing. And what that would allow a fabrication shop to do is use the AccuFast as much as possible, take advantage of the cycle time advantages. And if they do run into trouble with whatever reflectivity issues of the material, we can always revert back to touch sensing. So those are typically sold as a pair. Motosite 2D. So this one here, and we haven't done a whole lot with this, but if we have a type of weldment where we can't pick it up through normal touch sensing, then it is possible to use a conventional two-dimensional camera, take an image, and then determine where to weld. Expanded metal is a great example of this. So the camera will be tuned to take the image and then be able to determine where we want to put our tacks on the part. Here's a quick video of that. Okay, the last of our seam finding technologies is from a company called Servo Robot out of Quebec. These guys are recognized as the global leader in what they do. They've been around for many decades now, developing their products. Moto ISF or Moto I Seam Finder is essentially a laser line scan. The advantage here is that we can position the robot once over the start of the weld, perhaps once over the end of the weld, and take a quick laser line scan. It avoids having to move the robot around to actually trip a sensor to find out where the part is at. This is more capital, however. We typically charge $20,000 US to add this to the robot package. So if you can get away with your conventional touch sensing systems, that's what we usually go with. The iCubed is the high end of all of that. Quick video of there we go. So you can see in this video that the searching routine was much quicker even than the AccuFast that was being shown in the previous video. It does pick up cycle time, so it's a question of capital versus how much cycle time you wish to achieve. So everything we've talked about so far is about seam finding. So in other words, before we initiate the arc, before we start our weld, trying to find the weld joint. We do find that even doing that there is a requirement to, in real time, while we're welding, track the joint. And that could be because what's supposed to be a straight weld isn't in fact a straight weld due to part variance, or it could be a result of weld distortion. As we weld the part begins to move, but we need to track the joint as it moves. There are two basic technologies for this, the first being ComArc, or through the arc seam tracking. Again, this has been around for decades. It takes advantage of constant voltage MIG welding phenomenon. As we reduce stick out, in other words, the distance between the contact tip and the work, everything else being kept the same with the welding process, current will rise. So what we do is we take a current feedback from the welding package, and much like the touch sensing circuit, every modern welding power source that's set up for robotics will have the ability to give us current feedback in real time, whether it's a Miller, a Lincoln, a Fronius, an ESAB, what have you. So what we do is we start our weld and we deliberately weave the torch in the joint. And as we step off the center line of the joint and get to both toes of the weld and the stick out shortens, we see a current rise. And as we monitor that current relative to the robot position as we sweep back and forth across the joint, we can continually update the path as to where the center line of that joint is and effectively walk down the joint. The challenge with this, or the limitations of it, it works wonderful on horizontal fillets. If you're going to get into lap welds, it does not work so well on gauge material. You need to be 1/4 inch or thicker to really effectively ComArc it. So it's not the best option for a sheet metal application. Quick video of ComArc in action. So the weave is almost imperceptible, but it is necessary in order for us to see the current deltas as we move down the joint. And there you go. So we could continuously move that part around within obviously a window. As long as we can find the origin of the joint using touch sensing, we'd be able to have the robot adjust its path no matter what angle we put that fillet weld on. So the last technology we'll talk about today is what we call laser seam tracking. So this is seam tracking with the arc lit. The laser basically scans the joint ahead of the arc. What makes this difficult is trying to do a laser scan and get good clean feedback from where the part is at while the arc is lit. So again, this is a solution that comes from Servo Robot. This is really the cornerstone of their whole operation, and what they've been developing over the last 20, 30 years is tuning a laser to be able to filter out the pollution, the noise that comes off of the arc, determining the proper wavelengths, the proper frequencies of light to use for the laser so that it's not as susceptible to the arc. But it allows us a lot of flexibility in terms of what joints we can track. You basically program the laser system to know what kind of joint it's looking for. We can look at gap conditions, understand how well the part's been tacked together. If we need to slow the robot down to make up for a volume difference, or increase wire speed to make up for a volume difference in a joint, all of that can be tied into the system. So that's pretty much for my presentation. Anything else to add, Tyler? Anything else to wrap it up?
I think that's pretty good. We covered how to do things offline, how to create your path, and the reasons that you need to do seam finding and seam tracking once you've created that production part.
Okay, well, we would like to thank you again for joining this webinar. A copy of this recording will be made available shortly after for your convenience. If you have any questions, feel free to email either of your presenters, or you can email our info email that you can find on our website. If anyone sent any questions through the chat, we will also address those shortly after. Thank you, and hope to see you at the next webinar.
Thank you.